Ah, welcome. I know it's been a while since we've done this, but I went ahead and listened to what a lot of people were saying was successful and not successful from last week's work, and I thought it might make more sense for me to directly explain what to do instead of letting the instructions exist on the internet. So I put together a little presentation to explain what you need to know about Newton's third law of motion. The picture that you see here is of a Newton's cradle. A Newton's cradle is what we used in class the other week, where we would lift the weights on one side and one would go up and one would come down, and then one would go up on the other side and one would come down on the other side. This Newton's cradle is nothing more than a great example of Newton's third law. Newton's third law says that for every action, there's always an equal and opposite reaction. If we lifted one weight up, one weight would go up the other side. If they lifted two weights up here, then two weights would go up on the other side. Equal and opposite. Newton's third law of motion says that for every action, there's always an equal and opposite reaction. In terms of words, it's the simplest one to remember, but it's actually very complicated. For every action, there's always an equal and opposite reaction. When you think of the word action and reaction, you should think about forces. For every action force, there's always an equal and opposite reaction force. So here's a situation. We have the swimmer right here. And then what it's saying is that the force that her feet push on the wall is equal and opposite to the force that the wall pushes on her feet. Essentially, you can't push against something without pushing it back against you. Wait a minute, how does that make sense? Well, if you take your hand and you press it on the wall softly, you feel a little bit of force. If you take your hand and punch the wall, you feel a little bit more force. If you take your hand and really hit the wall, you feel even more force to the point where you could potentially injure your hand. Every force that you hit the wall's going to hit back with an equal and opposite. If I press against the table slowly, I can feel the table pressing against my fingers, and my fingers actually start to bend. If nothing pressed against your hand should just go through the table. But your hand doesn't go through the table because there's a force pushing back on you. You push on the table pushes on you. So one of the things that I wanted you to recognize from the videos last week was that forces must exist in pairs. For example, I have two pictures here, a hammer and nail. If you are taking a hammer and hitting a nail, right? When the hammer hits the nail, the hammer stops moving. Why is that? Well, the hammer hits the nail, so the nail goes into the wall or whatever you're hitting. But then the nail actually hits the hammer and causes the hammer to stop moving. The forces exist in equal and opposite pairs. So if you are walking up, so that's the first example right here. The hammer hits the nail hits the hammer. That's why the hammer stops moving. In the second example, where you have a guy walking on a boat, I don't know if you've ever been on a boat or on a pool or something, you try to walk on something floating in the water. If you walk to the left, as this guy's trying to doing, as his feet push it back, it pushes the boat backwards. You cannot walk unless you push something back. So when you walk on the floor, your feet pushes the floor and the floor pushes you forward. If the floor is not strong enough, you don't move forward. You would break through the floor. If the floor doesn't have enough friction, let's say the floor is very icy, you cannot walk because there's no force to push you forward. If you are floating in outer space, you cannot move because there's nothing to push against. All movement comes from forces. All movement comes from pushes and forces. If you have nothing to push against, you have no movement. All movement comes from pushes. So if you're floating in outer space, you could swing your arms all the way you want, any way which you want. It can swing your legs, your arms, but unless you have something to push against, you cannot move. All movement comes from pushing. So here are some examples of action-reaction forces that exist in the world. The car drives because the tires push on the road and the road pushes on the tires. Again, if the road is wet or icy, it can't push on the tires, and then you will slip and other things would take place. You may not be able to go, your tires could spin out, or you would just continue in a straight line motion, according to Newton's first law. Then how do you move in outer space if there's nothing to push against? Well, space works by using rockets. Rockets have a bunch of fuel inside the rocket right here. So rockets work in outer space because they push the fuel back as a gas. They push the gas back, and then the gas pushes the ship forward. Again, man pulls on the spring pulls on the man. Action, reaction. You cannot pull something without it pulling back on you. Now here's the weirdest one. If you drop something, the Earth is literally pulling on the ball. The Earth pulls on the ball. But the reaction force is not that, the ground hits the ball, but if the Earth pulls on the ball, then the ball pulls on the Earth. But when you drop something, it's not like the Earth runs up to meet the ball as it falls. No, because if it's an equal and opposite force, the Earth's mass is so huge, this little force of the ball pulling on the Earth isn't strong enough to move it. So that's what gravity is. Gravity is a pull on every object on the Earth. So gravity pulls on you, but you pull on the Earth. But your pull on the Earth isn't strong enough to move the Earth. The Earth's pull on you is strong enough to move you. Now every year someone always says, like, what if we got every single person in the world to stand in one spot and to jump up into the air? Could you move the Earth? Even still, even if you were to take the mass of all the people of the world, get into one spot and just jump, you would not be able to create enough force to actually push the Earth and cause the Earth to move. It is that much mass. So here's what I want you to do this week. That's what I want. Those concepts were what I wanted you to get last week. And I'm not sure how effective the Khan Academy was in getting them. And I'm not sure, it's kind of weird to think about it in that way. But I wanted you to kind of visualize that you cannot push something without it pushing back against you. You cannot hit something without it hitting back you. So, if someone comes up to you, if someone comes up to me and, it hits me in the face, they hit me in the face, but my face hits them back in the hand. So, we've really kind of hit each other. So, little Susie is floating next to Nellie Newton in outer space. The reason why we're drawing them in outer space is just so, let's pretend there's no friction, there's no anything else. We don't have to worry about anything else. So we got little Susie on the left, Nellie Newton on the right. That's little Susie because the hair. Okay? This is little Susie and Nellie Newton. This is the math that I want you to learn, and it's actually not that bad. So little Susie has a mass of 40 kilograms. So this is what we're going to do. Each person's going to have their own mass. Each person's going to have their own acceleration. Let's see if we can picture this. They're just floating next to each other. And if they give each other a push, he's going to move this way, and she's going to move this way. They're going to push, and they will move away from each other and just float in a straight line forever in outer space. So here is the general picture that you should kind of draw for all of Newton's third law problems. You have little Susie on the left, you have acceleration up top, mass on the bottom, acceleration up top, mass on the bottom, and then the arrow is the equal and opposite force. So it says little Susie is floating next to Nellie Newton in outer space. Little Susie has a mass of 40 kg. So underneath little Susie, I'm going to put 40 kg. Okay? That's her mass. Nellie Newton has a mass of 50 kg. Okay? Awesome. So her mass is 40, his mass is 50. If little Susie pushes Nellie Newton to the right with a force of 200 newtons, so this arrow is going to be to the right. I'm going to put 200 newtons right here. Okay? Newton's third law says she cannot push him 200 newtons unless he pushes her back with an equal and opposite force. In this case, 200 newtons. This is the key, you guys. Every time there is a push, the push must be equal and opposite. So if she's getting pushed, if she pushes him right 200 newtons, she is getting pushed left 200 newtons. Equal and opposite force. They experience the same force, but because they have different masses, they will have different accelerations. So what we're going to do is we're going to do the FEMA triangle, FMA. We're going to do a FEMA triangle for him, and we're going to do a FEMA triangle for her. Now, let's think about it. Okay, let's do Nellie Newton's acceleration first. He has a force of 200, and his mass is 50. 200 divided by 50 is 4, positive 4 m/s squared. She has a force of 200. It's actually negative 200. Wait, why is it negative 200? Because it's equal and opposite. This arrow is to the left, and left really means negative. Her mass is 40. Negative 200 divided by 40 is negative 5 meters per second squared. That's how you get their accelerations. And think about it. The person with more mass has less acceleration. The person with less mass has more acceleration. That's an inversely proportional relationship that we learned the other week we were in school. With more mass, you have less acceleration. It's a way of checking your work. Okay, let's do another sample problem. Well, let's look at this sample problem. Does it always have to be little Susie Nellie Newton? No, it can be, but it doesn't have to. If you've ever watched a movie that has cannons, like Pirates of the Caribbean or something, and every time they fire a cannon, the cannon goes back. That's true and according to Newton's third law. A recoil or kickback of a cannon is because the force that the cannon fires the cannonball is equal to the force that the cannonball pushes back on the cannon. So here we go. Let's look at this one. We've got two objects. We've got the cannon and we've got the cannonball. We have two objects. Now I said you are going to go ahead and have two objects. So I want you always to make this chart. M on the bottom, A on the top, arrow this way, arrow this way. Okay, so how do I know that the cannonball is on the right? Because it says the cannonball accelerates positive 40. Positive means right. So where it says the cannonball has an acceleration of positive 40, I'm going to go ahead and put A equals positive 40. It says the 600 kilogram cannon, so under the mass of the cannon, I'm going to do 600 right here. Okay, so far so good. All right. And what was the mass of the cannonball? Oh, 30. 30. Okay, so I have the, I don't have the force this time. I'm looking for the acceleration of the cannon. In order to get that, I'm going to need the force. Oh, but look. If I look at the cannonball, right, I can always use a FEMA. Force equals mass times acceleration. So I know that the force is going to be 30 times 40. What is 30 times 40? Ah, indeed, 1200. If this is 1200 to the right, that means this arrow has to be 1200 to the left. Equal and opposite forces. So I can use another FEMA triangle to go ahead and solve for the acceleration. Check it out. I'm going to go ahead and say 1200. Wait a minute. This 1200 is going left. That means it's negative. Divided by the mass of 600. Negative 1200 divided by 600. Negative 2 meters per second squared. Nice. That's it. That is all you have to do. Again, the object with more mass has less acceleration. The object with less mass has more acceleration. It's just a way of thinking about it. The acceleration here is negative. The acceleration here is positive. Acceleration here is negative. The acceleration here is positive because the cannon goes left, the cannonball goes right. Let's do one more problem together. Here we go. Let's see. Little Susie has a mass of 40 kilograms and pushes Nellie Newton, and he accelerates positive 3 meters per second. Okay, so you know what I'm going to do? Draw the line to separate the two people. Here's Nellie. Here's Susie. Awesome. Okay. Just get little Susie, Nellie Newton. Okay, now draw your generic chart. Mass equals acceleration equals mass equals. Arrow this way, arrow this way. Let's see what we can fill in. All right. Little Susie has a mass of 40. So where's this mass of little Susie? I'm going to put 40 kg. And Nellie Newton, and he accelerates positive 3. So Nellie's acceleration is positive 3 meters per second squared. Yes! If little Susie accelerated negative 6, okay? All right, so her acceleration is negative 6. Okay, let's see if we can do this. What is Nellie Newton's mass? So we're looking for the mass. We need to get the force. Okay, look at this. I have Susie's acceleration and mass. I can FEMA them. Force equals mass times acceleration. So her acceleration is negative 6. Her mass is 40. When I multiply them together, I get negative 240. So what I'm going to do is I'm just going to put 240 right here. It's next to a left arrow, which means the negative. So if she's going to the left with a force of 240 newtons, that means he's going to the right with a force of 240 newtons. And now, for the last step, I can just FEMA with his information to get the mass. The force is 240. The acceleration is 3. 240 divided by 3 is, of course, 80. He has a mass of 80 kilograms. If you have any thoughts, problems, questions, or concerns, I'm here. Please reach out to me. Your homework is going to be to do problems just like these 3 example problems. Feel free to pause and rewatch this video or email me if you have any questions or concerns. I wish you guys good luck, and I hope to see you all soon. Be well.